The fuel regulator is an electromechanical hydraulic pneumatic governing system for gas turbines manufactured between 1948 and 1970. This system takes electrical and pneumatic input signals to control the fuel flow rate to the combustion chambers of the gas turbine. This hydraulic output signal is known as variable control oil and can vary from 40 to 200 psig depending on the desired fuel flow. To help all three processors control more closely together, sometimes C is used to select a median value. This helps readjust R, S, and T. For example, let's say the turbine is controlling a certain parameter. R tells C that it is sending a value of 2. S sends a value of 3, and T sends a value of 5. C then communicates to each the median value, which is 3. Please note that this is a median value, not an average. R and T will then adjust closer to 3 so that each microprocessor is sharing the output more equally. The control system must limit the amount of fuel entering the turbine in order to maintain the normal operating conditions and to prevent exceeding the limitations. The amount of fuel needs to be limited to ensure a proper fuel-air mixture across the range of operation. Too much fuel results in over-temperature. Not enough fuel results in loss of flame in the combustors. When there is an upset in the control system, the fuel supplied to the combustors won't drop below the minimum fuel limit, also known as minimum blowout fuel. This is important so that the flame is maintained in the combustors, but energy is reduced to the turbine. In this example, the speed and load control loop is in control because it requires the least amount of fuel at 15%. If speed and load were to go up to 19%, however, temperature would then be in control because it requires the least amount of fuel. Please note that in the Mark I and Mark II control systems, VCE, Variable Control Electromotive Force, is used instead of FSR and is measured in volts rather than percentages. To give you a mechanical analogy, check valves behave the same way as diodes in electrical systems. In this analogy, a fixed pressure to the main manifold is provided by the supply tank. The pressure at the main manifold can be regulated by the check valves A, B, or C. For example, the pressure at point 1 is considered constant at 20 psi. If the pressure at points 2, 3, and 4 are higher than 20 psi, then there will be no control of the pressure at the main manifold. If the pressure at point 2 decreases to 18 psi, and the pressure at points 3 and 4 remain the same, then the pressure at the manifold will be brought down to 18 psi, and System A is controlling. As the operating conditions change, the pressure requirements at points 3 and 4 change. As the pressure, say, at point 3 drops below 18 psi, for example, 17 psi, the manifold pressure will be brought down to 17 psi, causing check valves A and C to close and check valve B to open. Therefore, System B is now controlling. The startup control loop controls the rate of fuel addition for several reasons: to establish flame in the combustors, to control the acceleration rate, and to control the rate of temperature change. Acceleration of the turbine rotor must be controlled so as not to exceed the allowable forces on the rotor. Exceeding the limit can cause heavy damage to the rotor. During startup, the airflow rates are low. If there is too much fuel added to the combustors while there isn't enough air, temperatures could get dangerously high, potentially damaging internal hardware. And high fluctuations in temperature can reduce the life of the internal hardware. Different materials heat at different rates, so the rate of temperature change must be limited at approximately 5 degrees per second. The startup control loop is an open loop that programs fuel to the gas turbine from the time the rotor starts turning until the turbine is at full speed. It selects a specific value based on the time in the sequence of startup and sends it to the minimum value gate. The startup control loop depends upon a predetermined signal corresponding to a predetermined condition. After warm-up, the accelerate signal allows the turbine to accelerate by gradually increasing the fuel level. This continues until the unit reaches full speed. Turbine shaft speed is measured and converted into a voltage signal or speed signal that is proportional to measured speed. To accomplish this, speed is sensed by magnetic pickups mounted near a 60-tooth wheel which is attached directly to the turbine shaft. Voltage pulses are generated by the pickups as the teeth of the wheel pass under them. The frequency of the pulses is proportional to speed. The control system converts this frequency input to a percentage of rated speed called TNH. The speed set point is the reference generated by the control system. This is the speed at which the turbine should be running. To give you an analogy, cruise control on a car functions in a similar way. Your actual speed may be 50 miles per hour, and your cruise control setting or the speed set point might be 55 miles per hour. Fuel will be added until the car reaches a speed of 55 miles per hour. This is what happens with a turbine as well. Isochronous operation is typically for mechanical drive turbines or power generation units that are isolated from the grid. In isochronous operation, the turbine control will try to maintain the called-for speed. If there is a load change, the actual speed will change. Under this operation, the speed and load control circuit will adjust the FSR so that the actual speed is the same as the called-for speed. Droop operation is typically used for generator drives connected to the grid. This allows them to share load changes that occur in proportion to their own maximum rating. This occurs regardless of what the actual load is on any particular machine at any time, as long as the unit remains online and does not exceed rated load. If there is a load change in the system, this is the formula used to determine what the new load would be for a particular generator based on the change. The present load plus the demand change multiplied by the unit rated load divided by the system rated load. This equals the new load. Let's take a look at this small power system as an example to see how droop operation affects changes in generator output. In this power system, there are three 60 Hz generators, each regulated with 4% droop. Take note of the rated load and the present load of each unit. Now, suppose the Acme Coffee Factory turns on its blowers and freezer system, creating a sudden 15 megawatt demand on the power system. Let's see what happens to the individual generators. Please click on the right arrow. Looking at generator number 1, the formula would be the present load, 731 megawatts, plus the demand change, 15 megawatts. This is multiplied by the unit rated load, 1000 megawatts, divided by the system rate load, 1575 megawatts. This gives you a new load of 740.5 megawatts. Please click on Back to continue. This is the formula used to calculate what the new system frequency will be for a given droop regulation and change in load. It is the present frequency minus the percent droop. This is multiplied by the demand change divided by the system total rated load. This is all then multiplied by the present frequency, giving you the new frequency. So in the case of this system, this is what the formula looks like, giving you a new frequency of 59.98 Hz. Please click on Back to continue. You've seen how the load changes on 3 units and how the frequency changes in the system based on a 15 megawatt demand. Now, let's look at how the speed of a single turbine generator unit is affected by droop operation. If a generator were running online at synchronous speed or at 60 Hz and gradually loaded to half load, speed would diminish along the sloped line shown. The speed at half load would be 3,528 RPM, and therefore at full load the unit speed would be 3,456 RPM. As you can see, the percent droop is the speed change, or 3,600 minus 3,456, divided by the rated speed of 3,600, all multiplied by 100. In this example, this equals 4% droop. You can also see the formula in terms of frequency. At any time during this speed reduction, an operator can restore the frequency to 60 Hz by raising the called-for speed set point to reach 3600 RPM. Fuel flow will slightly increase as the speed is increased. Typically, this change in the called-for speed set point occurs automatically by modern control systems. The temperature control loop serves an important function. It ensures that the internal components will not become overheated while still producing optimum power. The temperature control loop is a closed loop that compares the turbine operating temperature to a temperature set point. It reduces the FSR, fuel, when necessary to assure that the temperature limit is not exceeded. The actual temperature that is limited is the turbine firing temperature, but this is too hot to measure. However, in the exhaust plenum, the exhaust gases are much cooler and more uniformly mixed. Therefore, the temperature control loop uses exhaust temperature as measured by several thermocouples as feedback to control and monitor turbine temperature. Using this formula, the temperature control system calculates the turbine firing temperature. It is equal to the turbine exhaust temperature multiplied by the expansion ratio across the turbine divided by the barometric pressure. And this expansion ratio is elevated to some constant K. The use of this formula generates the relationship between exhaust temperature and compressor discharge pressure or fuel stroke reference as shown by the graph. The control system tries to maintain a temperature within the highlighted region. Should the temperature exceed the curve at low CPD or FSR, damage to the diffuser area may result. Should the temperature exceed the curve at higher CPD or FSR, damage to the first stage nozzle or turbine may result. The manual control loop is typically used through an initial startup or after a major outage. This is a way to manually limit fuel to prevent overfiring the machine. For example, here you can see a normal startup. However, manual control can take over, limiting the amount of fuel to the fuel system, as you see here. Manual control might be used if some work was done to the gas valve in the last outage and you want to make sure that it is calibrated correctly and functioning properly. The inlet guide vane, or IGV control loop, controls the fuel-to-air ratio. This provides compressor pulsation protection during startup and shutdown and exhaust temperature control in combined cycle applications. This graph shows the IGV schedule. At point A during startup, the IGVs start to open until they reach point B, minimum full speed angle. Should the IGVs open to the minimum full speed angle prior to point A, pulsation or compressor stall could occur, severely damaging the unit. The IGVs will maintain that angle until point C at partial load. This partial load position of the IGVs prevents operation which would result in negative pressure at the fifth stage extraction. In simple cycle operation, the IGVs will reach full open position at point D. In a combined cycle, they will remain at minimum full speed angle until point C1, then reach full open position at point D1. This delay in reaching full open position means that the exhaust temperature will be higher at partial loads, allowing for better heat recovery steam generator operation. This graph shows how the exhaust temperature varies for simple and combined cycle IGV operation. Note that IGV temperature control never exceeds the base temperature control set point. Servo valves are the primary means for positioning a valve. They supply hydraulic oil to the operating cylinder of a valve, such as the gas control valve. There are two basic types used, the Moog and the ABEX. For illustration purposes, we will describe the operation of an ABEX servo valve here. In its initial condition, with no signal from the control system, the fail-safe bias spring pushes the spool valve to the left, allowing hydraulic oil to close the cylinder. When the control system sends a signal to the servo valve telling it to open, The magnetic field in the torque motor changes, causing the jet pipe to tilt to the left. Here, oil is sent to the left side of the spool valve, pushing it to the right. Hydraulic oil is allowed to flow to the cylinder, causing the valve to open. Oil from the opposite side of the cylinder is allowed to dump to drain. When the control system wants to maintain the valve at some mid-stroke position, the jet tube directs oil to each side, causing no oil to be sent to or drained from the cylinder. Please click on Back. Linear variable differential transducers, or LVDTs, provide an analog AC voltage feedback to the control system. This voltage is linearly proportional to the position of the valve it is fixed to. The LVDT core moves as the valve stem moves, varying the feedback voltage. Please click on Back. This is a graphical representation of the gas fuel system and its components. First, we will explain the function of the key components and then show you how they function with the control system. The stop-speed ratio valve serves two functions. First, during an emergency trip or normal shutdown, the stop-speed ratio valve will close to stop all fuel flow to the turbine. Second, it provides pressure regulation of the gas supply. The ratio functions of the stop-speed ratio valve provide a regulated inlet pressure for the gas control valve relative to turbine speed. This ensures proper ignition and flame stability across the entire operation range of the unit. Please click on the right arrow to continue. The position of the gas control valve is proportional to the total called-for fuel flow. Therefore, the valve will meter the fuel used in the combustors by controlling the fuel flow. The fuel gas pressure transducer has a DC voltage output directly proportional to pressure input in PSIG. This transducer provides the control system with a feedback signal for the operational fuel gas pressure, or P2 pressure, between the stop-speed ratio and gas control valves. The fuel gas vent solenoid valve vents the volume between the stop-speed ratio valve and the gas control valve when the solenoid is de-energized. This valve is closed during operation. When it is open, it ensures that during the shutdown period, fuel gas pressure will not build up between the stop-speed ratio valve and that no fuel gas will leak past the closed gas control valve. Please click on the right arrow to continue. Now, let's examine how the control system interacts with the gas fuel system. Notice that gas is supplied up to the stop-speed ratio valve, but the valve is still closed. No hydraulic oil is supplied to the stop-speed ratio valve or to the gas control valve. When the control system initiates the firing sequence, a signal is sent to the trip solenoid valve and to the servo valve. The trip solenoid valve allows hydraulic control oil from the servo valve to flow to the servo actuator. The flow of hydraulic oil opens the stop-speed ratio valve. This moves the core of the LVDTs, sending a signal relative to valve position to the control system. As fuel gas fills the area between the servo valve and the gas control valve, the P2 pressure transmitters send a signal to the control system. Next, the control system sends a signal to the gas control valve servo, allowing hydraulic oil to force open the gas control valve. The gas control valve LVDTs provide position feedback to the control system. This position signal is compared to the required position based on the called-for fuel. As turbine shaft speed increases, the servos continue to receive signals to send more hydraulic oil to the valve cylinders, opening each valve and increasing the P2 and P3 pressure. The control and feedback signals continuously adjust each valve as required by the control system. This is a graphical representation of the liquid fuel system. First, we will explain the function of the key components and then show you how they function with the control system. The main liquid fuel pump is a positive displacement screw-type pump. It is driven by the gas turbine accessory gear and it delivers the required fuel to the combustion system. The flow divider apportions fuel oil to each of the fuel nozzles of the turbine. This ensures that each combustor receives the same amount of liquid fuel. The bypass valve meters the flow of fuel to the turbine by diverting excess fuel delivered by the pump and returning it to the pump inlet. Closing the bypass valve sends more fuel to the turbine while reducing the amount bypassed to the fuel pump inlet. The liquid fuel stop valve is an emergency valve. Operated from the protection system, this valve shuts off the supply of fuel to the turbine. Please click on the right arrow to continue. Now let's take a look to see how the control system interacts with the liquid fuel system components. Notice that liquid fuel is supplied up to the valve, but the valve is still closed. No hydraulic oil is supplied to the stop valve. When the control system initiates the firing sequence, a signal is sent to the trip solenoid valve, which allows hydraulic control oil to flow to the stop valve actuator. The hydraulic oil pressure opens the stop valve. This moves the arm of the limit switch, sending a signal to the control system that the valve is open. In turn, a signal is then sent to engage the liquid fuel pump clutch. An LVDT is used to tell the control system the position of the liquid fuel bypass valve. The control system will send a signal to the servo valve, which directs the appropriate amount of hydraulic oil to position the bypass valve. As the bypass valve closes, an increasing proportion of fuel is directed to the flow divider. Here, magnetic speed pickups sense the fuel flow change and send signals to the control system proportional to the amount of fuel being sent to the combustors. As turbine shaft speed and load increases, the servo valve continues to receive signals to send more hydraulic oil to the bypass valve cylinder, closing the valve. This sends more fuel to the combustors. The control and feedback signals continuously adjust the valve as required by the control system. Please click on Previous Menu to continue. Some turbines are designed to operate on either liquid fuel or gas fuel or both. This is known as a dual fuel system. In order to change the type of fuel the turbine is operating on, the control system initiates a fuel transfer. Let's say that the turbine is operating on liquid fuel. When the control system gets a signal to transfer to gas fuel, the gas stop and control valves open, allowing gas fuel to flow to the combustors. As the amount of fuel gas is increased, the amount of liquid fuel is decreased in order to maintain the speed or load conditions. When the turbine is operating on 100% gas fuel, the liquid fuel system is shut down and the liquid fuel lines are continuously purged with air. Over-temperature protection protects the gas turbine from damage caused by overfiring. Under normal operating conditions, the exhaust temperature control system regulates fuel flow when the firing temperature limit is reached. However, if the exhaust temperature and the fuel flow exceed control limits, the over-temperature protection system provides an alarm prior to tripping the gas turbine. If the temperature should still increase, the gas turbine is tripped. The specific alarm or trip over temperature set points for any unit are found in the unit's control specifications. Please click on Back to continue. The overspeed protection system is designed to protect the gas turbine against possible damage caused by overspeeding of the turbine shaft. Typically, the overspeed protection system consists of a primary and secondary or backup system for the normal control shutdown features. The primary overspeed protection system is the electronic system and consists of magnetic pickups to sense turbine speed. The secondary system is mechanical and consists of the overspeed bolt assembly in the accessory gear shaft and the overspeed trip mechanism. Both systems operate to trip the fuel oil stop valve and the fuel gas speed stop ratio valve. Please click on the right arrow to continue. The electronic overspeed protection function is performed as shown here. The turbine speed signal derived from the magnetic pickup sensors is compared to an overspeed set point. When the turbine speed signal exceeds the set point, the overspeed trip signal is transmitted to the master protective circuit to shut down the turbine. An electrical overspeed trip message will be displayed. Please click on Back. An overspeed bolt assembly mounted in the accessory gear shaft is used to sense the overspeed of the gas turbine. As the shaft speed increases, centrifugal forces acting on the bolt are balanced by the spring force within the bolt assembly, and the bolt remains seated. Further increase of the shaft speed causes the centrifugal force on the bolt to exceed the spring force, and the bolt moves outward and trips the overspeed trip mechanism. Please click on the right arrow. The overspeed trip mechanism for the turbine shaft is also mounted in the accessory gear adjacent to the overspeed bolt assembly. When actuated, the overspeed bolt assembly trips the latching trip finger of the overspeed trip mechanism. This action releases the trip valve in the mechanism and dumps the OLT hydraulic trip system pressure to atmospheric pressure. This in turn causes the oil in the pilot dump valve cylinder of the gas stop ratio valve assembly to return to atmospheric pressure, closing the valve. This ends our explanation of the overspeed protection system. Please click on Back to continue. The flame detectors perform two functions, one in the sequential system and the other in the protective system. During a normal startup, the flame detectors indicate when a flame has been established in the combustion chamber and allow the startup sequence to continue. Should the flame detectors indicate a loss of flame condition while the gas turbine is running, fuel is immediately shut off. This avoids possible accumulation of an explosive mixture in the turbine. The flame detector system, used with the Speedtronic system, detects flame by sensing ultraviolet radiation. Such radiation results from the combustion of hydrocarbon fuels and is more reliably detected than visible light, which varies in color and intensity. On non-DLN units, the flame detection system typically consists of 2 to 4 independent detectors per set of interconnected combustion chambers. Please click on Back to continue. The vibration protection system of a gas turbine unit is composed of several independent vibration channels. Each channel detects excessive vibration by means of a pickup mounted on predetermined bearing housings. The vibration detectors generate small current outputs by passing a magnet through a fixed coil, and therefore no excitation current is necessary. If a predetermined vibration level is exceeded, it first alarms at typically 0.5 inches per second, and then would trip if vibration exceeded 1 inch per second. Please click on Back to continue.